Hey everyone. In the last video, we looked at how we can estimate the empty weight of the aircraft. In this video, we'll look at how we can estimate the fuel weight of the aircraft through mission analysis. So mission analysis is something that we have to do to know whether or not our aircraft will have enough fuel to complete the mission, right? So, but that required amount of fuel really depends on the type of mission and the aerodynamics of the aircraft and the engine fuel consumption, right? So if your engine is consuming more fuel, well, you need more fuel in your tanks, right? And that will add to your weight of the aircraft, right? So here are some examples of the mission profiles for different aircraft types. You get the simple cruise where the aircraft will take off, climb to an altitude, and then they cruise out, to a certain range, and then descent, and you do a loiter. Loiter is basically like holding the pattern, above a certain field or certain area, right before it can land. For a general aviation aircraft, that can be like holding a pattern above the runway. For commercial aircraft, if the traffic, if the airport traffic is high, then most the air traffic control ask the airplane to basically loiter before they can actually land, right? So here, that's the simple legs of the missions for a simple cruise. And then you got the commercial transport, you get the low level strike where you get the loiter and the drop bombs or any packages, um, right? And then come back and land. And then you get the air superiority where you have the combat as well, right? So here are some of the typical mission profiles, but it really depends on what you want the aircraft to do, what your aircraft to do. So right, this is something that you will get out of the requirements stage. So by the time you start this assignment, you'll have a better you should know at least in a cursory level what the mission profile for your aircraft is going to look like, right? So in general sense, you have the altitude versus distance, right? We have the different phases of the mission, and our goal here is just to look at, what would be the fuel consumption of the aircraft at each and every phase of the mission, right? And we will do some, rule of thumb estimation. We'll use some equations to estimate the fuel burn, but again, everything that we're going to talk about is in a generic sense. So for specific, a guess or specific like values, that we're going to need for doing the mission analysis can be found, in your respective textbooks. All right, so make sure to take a look at those as well. But we're going to talk about some generic ways to estimate the fuel, and then you guys can look into the books to see to find more accurate information on the values that you have to use. All right. So one thing that you have to do, no matter what aircraft you're designing, is that you need to account for contingencies, emergencies, reserves, etc. Right. And because most of the government organization, either it's a FAA or military, they have requirements on the reserve fuel and contingencies, right? So that's something that you need to look. So for FAA, for general aviation aircraft, by after you complete the mission, there should be enough fuel left in your tank for like a half an hour flight more. Okay, so that's from the FAA for general aviation, but basically look at it for different types of aircraft you're designing and should be accounted for in your fuel weight estimation as well. So this is something that you have to adhere, and not even the customer or the manufacturer can change this, right? This is constant. So we need to adhere to these requirements. All right. So let's take a simple cruise, and then we'll sort of walk through the process of how we can do the mission analysis. Right. As I said, the simple cruise has there's about 5 legs in the mission. Right. First is a warm up and takeoff. Second is the climb. Third is a cruise, and then the fourth is loiter, and the fifth is basically land, right? And we'll be estimating what would be the fuel burn, or the weight of the aircraft at each stage of this mission, right? So we can assign some nomenclatures here. W naught is the beginning takeoff weight, which is the gross takeoff weight, right? W1 is the weight at the end of warm-up takeoff. If it's an aircraft, if it's a general aviation commercial, there's a pre-flight as well. W2 is basically weight at the end of the climb, right? W3 is weight at the end of the cruise. W4 is the weight at the end of loiter, um, and weight W5 is the weight at the end of like the landing mission. All right. So therefore, like our we can express all of this in terms of ratios, right? So the final weight divided by the initial weight of the aircraft is nothing but W5 by W0, W5 by W4 times W4 by W3, W3 by W2 times W2 by W1 times W1 by W0. So if we know what this weight fraction is, then we can get an estimate for what is the final weight of the aircraft is going to be, right? And that's pretty much what we are trying to look for. And if we know the final weight and if we know the initial weight, we can subtract those two and get an estimate for a fuel, right? So the difference will just be the fuel weight. And this is assuming you're not dropping any packages or any payload during the mission. Okay, and if you're doing that, well, you're going to have to account for that as well, right? So, in this mission, we're assuming there's no other weights being dropped. So the difference between the final and the initial weight is basically the fuel weight. Okay, so now let's look at the engine phase one, which is the engine start and takeoff, right? The start of the engine's taxi, pre-flight, and takeoff is basically what we need to account for at this phase, right? So a good rule of thumb is that at this phase, you can assume that the aircraft burns about 2.5% to 3% of the takeoff weight in fuel, right? So in other words, W1 by W0 can be 0.97 or 0.975. Just pick a number for it. But 2.53% is basically kind of what we are looking for. But again, it really depends on the aircraft that you're designing as well. So you may get a reasonable estimate for this, if you look at the particular textbooks. Okay, this is again for a generic sense. The phase two is where you climb and accelerate to cruise. So accelerate to cruise means that you require a certain cruise velocity, and you use the climb phase to basically achieve that, right? So by the time you accelerate to a cruise, depending on your cruise velocity and what speed and altitude that you're required to achieve, you will basically consume fuel depending on that, right? So for low performance aircraft with a cruise Mach number of less than 0.4, that burn is not really significant, right? Maybe 0.99, 0.98. But for high performance aircraft, well, the way I define high performance here is with cruise Mach number greater than 0.4, which again, most aircraft except for general aviation do, right? They always have a cruise Mach number greater than 0.4, and altitudes greater than 10,000 feet. So in that case, you can actually use this graph to estimate what would be the fuel burn, during that climb phase, right? So you can see that at lower Mach numbers or lower cruise Mach numbers, right, 0.2 to 0.4, you're really close to 0.99, you're really close to 1, right? But as you increase the cruise Mach number, you start decreasing the weight fractions here, right? Because, right, if you want to cruise to Mach 2, well, that's kind of gives you about 0.9. So you lose 10% of the weight of the aircraft in fuel by the time you achieve cruise Mach number, right, of 2. Right, so this, again, you have different aircraft examples here, like you have the Lockheed SR-71, right? By the time it reaches a cruise Mach number of 3, it actually lost about 20% of the weight of the aircraft in fuel, right? And so one of the reasons why it needs refueling as the airplane is flying, it needs mid-air refuel to complete this mission, right? And again, SR-71 is a unique bird because it never takes off at full weight. The aircraft should have to refuel as soon as it takes off as well, right? So it only has enough fuel to basically take off and reach a certain altitude. And in order to finish the mission, it always needs a refueling tank, all right? So, but that's an odd bird. But here, if you look at the F-15s, again, a lightweight fighter, so it's the cruise Mach number is about like 0.7 or 0.9, right? So that the fraction weight fraction here is not that significant, right? So it's basically the idea is that you estimate the weight fraction at this leg using this data, right? Or using this graph. I took this graph from Nikolai, so you can also see this graph in your textbook, right? I mean, you can definitely you can either plot digitize it, or you can just look at from this graph and make an estimation. Keep in mind that the x-axis is not a linear scale, it's a log scale, right? And the y-axis is basically linear, so you're gonna have to account for that, right? So this is basically phase two, climb to accelerate to cruise condition in a phase. And the next phase is basically your cruise out, right? We want to estimate, if your aircraft is flying at a certain cruise speed, a certain range, what would be the weight of the aircraft, after it actually done cruising, right? So that means, we need to estimate of cruise speed, altitude, the aircraft AR, because aspect ratio really depends on, the range depends on the aspect ratio, right? The wing speed and the cruise fuel consumption. And some of this should come from your requirements and historical buildup because, right, when you set the requirements, you basically set what cruise speed that you want out of the aircraft and what should be your aspect ratio. It may not be a requirement for, an aspect ratio may not be a requirement for the aircraft, but this is something you can get from historical buildup to see, like, what is the general AR range for the aircraft type that you're designing, right? And wing speed and cruise fuel consumption, it's something that you need to assume as well, right? So again, now we can estimate the fuel burn used in this leg, in the cruise leg, using the Brugge range equation, right? For turboprop or turbojet, the equation is given by here. So range R equals V, the cruise velocity, divided by C is the thrust specific fuel consumption. L over D is the lift by drag, which is the aerodynamic efficiency of the aircraft, times the ln of weight W2 by W3. What we are really interested is in the weight fraction. We want to know what is the weight of the aircraft after it's done cruising. So we can rearrange this equation in this form, right? You get W3 by W2 equals exponent to the power minus R times C by V times 1 by L over D, right? This is for the turbojet turboprop. For the prop aircraft, you have the similar equation, but you don't have the cruise velocity. It really depends on your efficiency, the propeller efficiency. Okay? And the specific fuel consumption you have is not the same as the thrust specific fuel consumption, but it's a brake specific fuel consumption, right? And you can rearrange that to get W3 by W2 as well. So here are the nomenclature for the variables used in these equations, right? We discussed all of this, right? So again, one thing that you have to make sure is you have to make sure that the units match. You got to make sure to use the right units for the specific fuel consumption, the velocity, and the range, etc. Right? So everything in this equations. Well, let's start with the range. Range should come from your requirements, right? You want to know or specify what is the range for your aircraft is going to be, right? And cruise velocity is something that you have to know as well. Right? You want the aircraft to cruise at this speed, so that's something that comes out of the requirements. Now there are two other variables, right? One is the specific fuel consumption, and the other is aerodynamic efficiency, which is L over D, which is what we're going to be assuming or estimating to be able to get this weight fraction. Right. So one thing to note, if you need a maximum range R of the aircraft, then your L over D should be close to the maximum, or it should be the maximum L over D possible, right? So that means that you're getting this is the stage where you sort of like set a goal for what your max L over D for your aircraft needs to be, right? So again, that will come through estimation. So that's what we're going to talk about, right? So we're going to talk about how to estimate the L over D here. So here, and I took this from Raymer. You have different equations for different types. You get the maximum jet range at constant throttle, maximum jet range at constant altitude, right, and maximum propel endurance L over D. So these are L over D at different settings here, right? And you can see that even if you just ignore what's in the center and actually look at in the back right there, so it is a fraction of the L over D max, right? So again, so for constant throttle is 0.94 times L over D max. For constant altitude is 0.86 times L over D max, etc. Right. So now, if we were to use these values to estimate the L over D during cruise or to loiter, what we need is we need an estimate for the L over D max. Correct. So again, estimating L over D max, there are two methods. First, you can actually do through CD0, right? For example, if you recall the performance homework, we derived an expression for the L over D max and the CD naught, right? And it's basically like, the L over D max really dependent on the CD0, right? And K, where K is the 1 over pi EAR. So this is again where you have to make an estimation for what your oswald efficiency is going to be and what your aspect ratio is going to be. Again, you don't have to pick a number out of the hat. Please use your historical buildup. Like this is exactly why we are doing the historical buildup, because it'll give you a good platform to assume values on. So right? This is something reasonable, right? If you're designing a high endurance aircraft, then if you pick an AR of one, well, that's not right, right? Because usually high endurance aircraft will have aspect ratios all the way from like 8 to 10 and more, right? So this sort of information is what you will get out of the historical buildup, which you can use to arrive at a good estimate to start with. Otherwise, you will be doing a lot of iterations back and forth, which will waste a lot of time. So that's why the historical buildup is very important, right? And again, you need to estimate a value for oswald efficiency as well. That's also something that you can back out from your historical buildup, right? But at the end of the day, you have to assume a CD0 value for this as well, right? And CD0 values, depending on what type of aircraft you're designing, if you look at those textbooks, you will have, I can guarantee you will find a table in the book where it kind of tells you some of the CD0 values for the similar aircraft types. Okay, you can find on any design textbooks, right? So you can, but the idea is that you basically start with an estimate, right? What it is the CD0 that you want, and by doing this analysis, what you're assuming is that okay, you're trying to get this CD0 out of your aircraft. Whether or not it's possible, we'll see in the aero buildup. But for now, you're gonna have to make an estimation of what the CD0 is. Again, you can rely on historical data, and you can rely on the textbooks for make a good assumption, right? And the second method, Raymer does it through vetted area approach. I think the first method is Nikolai, and second method is Raymer. So LOD max can be assumed by an aspect ratio. And this is an actual aspect ratio. Here's a vetted aspect ratio, right? The vetted aspect ratio is nothing but B squared by S vet, which, the relationship between the vetted aspect ratio and the regular aspect ratio is shown by this equation right here, right? Vetted aspect ratio is nothing but regular aspect ratio divided by S vetted area divided by the reference area. So vetted area is like the surface area of the aircraft, right? And the reference area is the planform area of the aircraft. And Raymer does gives different numbers for these coefficients KLD. KLD is 15.5 civil-jets, 14 for military jets, 11 for retractable plot, and so on. And the area ratio, the SVET by SREF, can be found in here. On the x-axis, you have the vetted aspect ratio, and y-axis you have the L over D. And basically, you can see that it's he assumes a different slope for different type of aircraft. Right? Again, all of this is in a generic sense, but again, you can find specific values for the aircraft you want to design in your textbooks. Right. So again, these are two different methods, and again, which one is right? Well, that's that's a tough question, right? Because these are different methods that exist. It's not like one method is right than the other. It's something that you're gonna have to choose, all right, depending on what type of aircraft that you're designing. So this is again estimating L by D, right? If you know the L over D max, then you can use that to estimate L over D, and you can use that to estimate your weight fractions for your cruise. Another thing that's actually in the equation is C, which is a thrust specific and brake specific fuel consumption that you also need to estimate, right? So here is a picture from Torrent Peak, I believe. So where it kind of mentions the thrust specific fuel consumption as a function of like years. So you can see how the thrust specific fuel consumption has actually gone down over the years. Um, but this is just a general trend, right? But for your aircraft that you want to design, here are some of the like values that I pulled from Raymer. Right? So, for a different type of aircraft or different type of like engines, and then you have the prop as well. One thing to note again, depending on what textbook you're referring, they may follow a SI units or English units, but you always have to be wary about you always be like looking for whether or not you have the right units to work with. All right. So if you don't have the right units, you have to spend time converting them to the right units so that when you plug it into the equation, they actually match and the units match. Okay. Again, units is very, very important in the design process. So, make sure to always be looking out for, the units. Okay. So here, some of the values that you can actually use for cruise and loiter. But you can also refer to Appendix J of Nikolai, where he has a ton of information on like jet engines, especially like the turbofans, as you can see here, and the specific fuel consumptions and all of that, it's in there. So again, there are information out there which again you just need to find, and you need to be able to estimate a good value to start with. Okay, so again, please make sure to refer those books so that you get a better idea, right? Okay, so once you do that, then you can actually find W3 by W2, and the next phase is basically loiter. Well, there's a descent phase, but we can in the descent phase you will see that it doesn't consume that much fuel because you're literally like gliding the aircraft down, right? But what consumes fuel is the loiter phase as well. So that's what we're going to talk about. Phase 4 is the loiter. So the loiter is how fast and how long can the airplane stay in air, right? And that can be estimated by the endurance equation, which has a similar flavor as the range equation. So the endurance of the aircraft for the jet aircraft is 1 over C L over times L over D times ln 4 W4 by W5. We can swap that for W5 by W4. That's a weight fraction that we need. We can write that in terms of this, right? So we have seen all of the variables in the range equation. E here is just for the endurance. All right. For the prop aircraft, you don't have thrust specific fuel consumption. You got the brake specific fuel consumption here, and eta is your prop efficiency, right? We can solve for W5, W4 in this equation as well and get a value, right? So endurance, again, from the requirement, and C prop, you estimate. L over D is something that you estimate as well from the previous step, right? And this will eventually give you an idea of what the loiter weight fraction is going to look like. Okay. The last phase is basically land. Not a lot of fuel is actually used while landing slash descending, because you literally like gliding the aircraft down. So it's a good estimate will be just to do like a 0.5%, or like W6 to W5 is 0.995. Okay, so that's pretty much a simple cruise, mission analysis. But depending on what type of aircraft you'll have some additional phases as well, like a high speed dash. You're going from a certain cruise velocity to a really high velocity. Say, you want to go from Mach 0.9 to Mach 2.5, right? Then you can estimate the fuel burn for those high speed dash by using this graph as well. So we'll start with the Mach 0.9. You know what that estimate is, right? Say that's around 0.975. For Mach 2.5, again, this is a log scale, right? So the 2.5 can be close. So 2.5, that can be around like 0.91, right? So if you want to determine the fuel burn, after and before this leg, you can estimate it by using this fraction, right? 0.91 divided by 0.975 will give you a fraction of fuel burn, a fraction of the reduction in weight, um, you know, uh, depending on the values that you get from this graph, right? So again, this is something that you may need in your requirements, in your mission, right? Because you want to cruise faster, you want to do a high speed dash and get to your area faster, um, right? So this is something that you may need you may need to do depending on what type of mission you have. Right. Another, if you are designing a fighter, then obviously you will have a combat, right? So if we want to do the combat, they usually specify in the requirement phase. You will have to specify one or either of these requirements, or and both of them, right? So basically, the first one is a specified number of minutes at max power and a particular Mach number and altitude, and specified number of turns at max power and a maximum load factor m and altitude. So load factor is very important for any fighter because it needs to sustain a high G loading or high turn load factor. For example, like F-18s can sustain up to 7 Gs during a tight turn, right? So that's kind of the upper G limit, and there's a lower G limit as well that you may need to set in your requirement stage. Okay, so depending on this, you can estimate the combat fuel to be thrust specific fuel consumption times the maximum thrust times the time. So the time is nothing but the number of turns, which are the 360 degrees divided by the turn rate. And the turn rate is given by the load factor, right? So that means, say, if you want the aircraft to do 7 Gs at a certain velocities, then you will know your turn rate. And depending on the maximum number of turns, you can do like you can calculate the turn time. And from there, depending on the type of engine you have and the thrust specific fuel consumption, you can estimate the combat fuel, right? So you're basically going backwards, right? So this is again something that you may need to estimate for, you know, for you know if you have combat, in your mission, right? So now let's put it all together. You got the final weight divided by the initial weight is given by the product of the ratios. So the fuel weight fraction is nothing but the fuel weight is nothing but the initial weight minus the final weight, right? That's basically fuel. Again, this is assuming we don't drop any packages or bombs or anything in between, right? And that should be equal. If we simplify this equation, it will basically equal weight of the fuel divided by the initial weight equals 1 minus weight final divided by the initial weight. So it's also important, as I mentioned previously, it's important to account for the reserve and the trapped fuel as well, right? So the W fuel by W naught equals 1 plus reserve plus trapped fuel times 1 minus W final by W naught. Right? This is something that, this something you're gonna have to account for, so that, you basically like adhere to the requirements set by FAA and military, right? Um, Rearranging this equation, you'll actually get W fuel equals, the entire product times W naught. So what we have achieved here is that we have a expression for fuel weight in terms of the takeoff weight, right? If you recall our empty weight discussion, we have similar relationships too. And we have empty weight as a function of takeoff weight. Now we arrive at an expression for fuel weight in terms of takeoff weight. Now let's just put it all together. Like, our weight breakdown is basically this, right? W naught equals crew plus payload plus fuel plus empty. Um, the crew and payload weight is known from the requirements, and we just derived an expression for the fuel weight. From our last video, we looked at the empty weight, right? You can, this is from Nikolai, this is from Raymer, and you can also get one from your historical buildup, right? But the point here is that empty weight can be expressed as a function of the takeoff weight, right? So we're substituting all of this, you get, we get the total takeoff weight equals, the crew plus payload plus the fuel plus the empty weight. Now the fuel weight and the empty weight is a function of W naught, right? So this is exactly why we need to do an iteration, because say you assume a W naught, you end up getting a fuel weight, you end up getting an empty weight, and if you add it all together, well, that may not be equal to the payload, the weight that you started with, right? So that's why then you have to go back and change that W naught again. And you do the iteration until the left-hand side equals to the right-hand side. So graphically, you can say, for example, it gives a good estimate. So the x-axis, you have the guessed W naught, y-axis, you have the calculated. Say you start with an estimate for 40,000 pounds takeoff weight, but the calculator seems to be like 60,000. So now you basically slowly increase it until you converge to a solution, right? So it is at this point where you will, you should, where you basically stop the iteration, where you say, hey, we converge. And now, but after this, you have a good idea for the empty weight, the fuel weight of the aircraft, right? And again, this is very important because without the total takeoff weight, we can't size our wings, right? We need to know what the total takeoff weight is going to be so that we can design the wings accordingly, right? And when we do the constraints, we'll also determine the engines, the thrust that you need to achieve the requirements and meet the constraints. That's also again depends on the takeoff weight as well. So there are two things that are depending on the takeoff weight. One is the wing size and the engines that you need. So this is very crucial, before we end up sizing our wings and engines. All right. So just to give you a good example of a weight breakdown for typical loading, you got the left-hand side is the bombers, and you got the fighters in here, right? This is the weight in pounds. You see the weight breakdown. This can be in its dimensional, so it can be a little hard to read. But let me put it in terms of percentage of gross takeoff weight. So you can see that for bombers, right, the maximum takeoff, the highest percentage is taken by fuel, right? Because, well, bombers usually have a longer range, and for that they need a lot of fuel, right? And empty weight is sort of like lower or even equivalent to other weights, right? The payload weights, it's basically the bombs right here, right, and the crew. For the fighter, it's kind of the opposite. Fighters carry a lot of weight. The empty weight. Look at the F-111, F-117 JSF. The empty weight is basically a lot, right? This is mainly because it carries a lot of systems that needs to support its mission. And F-111 is particularly interesting because if you look at the payload weight, it's like few 2%, but F-111 Aardvark has a variable sweep. So there is a lot of weight that goes into the empty weight because it needs to do the variable sweep. But at the end of the day, it can only carry so much payload, right? But for to carry that small 10% of the payload, it needs all of this weight, to go with it, right? So depending on the range. So the idea here is that depending on what your requirement and the mission profile is, you're gonna get a variety. You're gonna get a weight breakdown accordingly, right? But there are trends that you can actually see. Like bombers usually the fuel payload is fuel load is a lot, and then for fighters, like empty weight is a lot. So this is again one of the reasons why historical buildup will come in handy, because when you get an expression for this, you find the fuel weight fraction, empty weight fraction. It should be roughly in the same order of magnitude as you have from your historical breakdown. If you see something out of the ordinary, then you may have done something wrong. Okay, so make sure to, again, this is also a scenario where the historical buildup will actually come in handy, because again, this is otherwise how would you know the answer you got makes sense or not, right? So this is this is important. So this is basically for a bomber, but you can ignore that. I think you got the point from this plot, right? So in the next video, we'll talk about constraints. But hopefully by now you know how to estimate the empty weight and the fuel weight, right? Which is exactly what your next step of the aircraft design process is. All right, I'll see you in the next video.